What if the man who defined our modern universe, the architect of the physical laws that govern our reality, wasn't even expected to survive his first day? What if the mind that would calculate the motion of the planets was born so prematurely, so fragile, that the women attending his birth believed he wouldn't live to see the sunset? This is not hyperbole. This is the precarious beginning of Isaac Newton. Born on Christmas Day, 1642, in the tiny hamlet of Woolsthorpe, England, he entered a world convulsed by civil war. He was, by his own mother's account, small enough to fit inside a quart-sized mug. His father, also named Isaac, was already dead, buried 3 months before his son's desperate, grasping arrival. This infant, fighting for breath in a cold farmhouse, represented one of the greatest paradoxes in human history. A life that began at the very edge of oblivion, yet would proceed to expand the boundaries of human knowledge to the very edge of the cosmos. The sheer improbability of his survival is a chilling prelude to the magnitude of the life he would lead. A life that would tear down to millennia of established philosophy and replace it with a universe of breathtaking mathematical certainty. If you find this exploration into the foundations of our reality compelling, and wish to support our journey into the minds of other great thinkers, please take a moment to show your support. Hitting the like button helps this story reach more people. Subscribing to the channel ensures you won't miss our next deep dive, and sharing this video with others who appreciate history and science is the single best way to help us grow. Your engagement makes these complex stories possible, so thank you for being a critical part of our community. The psychological profile of this solitary genius was forged in the fires of that early fragility and, more profoundly, in abandonment. Born prematurely in 1642, his father already dead, he was left with his grandmother at the age of 3 when his mother, Hannah Askow, remarried. Her new husband, the Reverend Barnabas Smith, was a wealthy but older man who wanted a wife, but explicitly did not want a stepson. For the next 8 years, Isaac was separated from his mother, living in the care of his grandmother, while his mother raised a new family in a nearby village. This abandonment carved a wound in Newton's psyche that would never heal. It forged a man who was pathologically untrusting, fiercely independent, secretive, obsessive, and incapable of intimacy. We see the rage of this rejection in a list of sins he compiled as a teenager, a chilling entry that reads, "Threatening my father and Mother Smith to burn them and the house over them." This was not the idle fantasy of a moody child. It was the cold, recorded fury of a mind that already processed the world through systematic, written analysis. The solitary, obsessive genius who would later lock himself away to decode the universe was not a choice. It was a defense mechanism created in the crucible of his childhood. Before Newton, what did the word science even truly mean? In the mid-17th century, the term didn't exist as we know it. What existed was natural philosophy, and it was not a practice of discovery, but a discipline of rhetoric. It was, at its core, a 2,000-year-old argument based on a library of ancient books. The unquestioned authority was Aristotle, whose ideas had been absorbed and sanctified by the medieval church. According to this scholastic tradition, the universe was understood through deduction from first principles. Why does a rock fall? Because its nature is to seek the center of the universe, which is the Earth. Why do the planets move? Because they are embedded in crystalline celestial spheres, pushed by angels or a prime mover. Truth was not found by observing the world. It was found by debating the texts. It was a closed system, a world of qualities: hot, cold, wet, dry, and purposes. Not a world of quantities and laws. To challenge Aristotle was not just an intellectual error, it was a form of heresy. Into this rigid, stagnant intellectual world walked the young Isaac Newton, arriving at Trinity College, Cambridge, in 1661. The official curriculum was a rigid diet of this very Aristotelian philosophy. But Newton, the solitary and intellectually voracious student, instantly rejected it. He found the debates of Aristotle and the purely logical, non-experimental world of René Descartes to be mere philosophy, not truth. In his private notebook, which he titled Questions Quaedam Philosophicae, or Certain Philosophical Questions, he wrote a defiant motto beneath the title: Plato is my friend, Aristotle is my friend, but my best friend is truth. He rejected the path of passive learning and began a ruthless, self-directed program of study, devouring the new philosophy of Galileo, the atomism of Gassendi, the astronomy of Kepler, and the geometry of his own mentor, Isaac Barrow. He instinctively understood that truth was not to be found in philosophical debate or logical assertions. It was to be found in the cold, hard, irrefutable language of rigorous mathematics. He wasn't just learning. He was sharpening the weapons he would need to dismantle the old world. How does a global pandemic, a microscopic agent of death that brings a nation to its knees, become the catalyst for the single greatest burst of individual human genius in history? It is a terrifying and profound question. The Great Plague of 1665 was a biological firestorm, a resurgence of the Black Death that swept through London, killing nearly a quarter of its population. The air was thick with the smoke of juniper fires. The streets echoed with the tolling of bells and the grim cry of "Bring out your dead." Fear was total. In response to the encroaching horror, the University of Cambridge did the only thing it could. It shut its doors, sending its students home to wait out the apocalypse. For Isaac Newton, this was not a vacation. It was unenforced exile, a flight from death that sent him back to the isolated farmhouse where he was born, Woolsthorpe Manor. The plague of 1665 closed Cambridge, forcing Newton into 2 years of intellectual isolation at Woolsthorpe Manor from 1665 to 1666. This solitude, this period of intense, unbroken, and obsessive focus became his annus mirabilis, his year of wonders, while the world outside was consumed by death and fear. Newton's mind was consumed by creation. In that farmhouse, with only his books, his thoughts, and a few basic tools, he laid the foundations for his entire life's work. He invented the method of fluxions, the mathematical language of change that we now call calculus. He conducted his famous prism experiments, plunging his room into darkness to dissect the very nature of light and color, proving white light was a composite, and, most legendarily, as he sat in the garden, he watched an apple fall and began to formulate the core principles of universal gravitation. When he finally returned to Cambridge 2 years later, The plague subsided. He was, in secret, already the world's greatest mathematician and physicist. How do you even begin to describe a falling apple or the sweeping arc of an orbiting planet if the mathematics for change itself doesn't even exist? This was the fundamental barrier of 17th century science. The geometry inherited from the ancient Greeks, the geometry of Euclid, was a masterpiece of a static world. It was perfect for measuring a field, the angles of a triangle, or the volume of a sphere. But the real world, the world Newton was obsessed with, was not static. It was a world of motion, of flux, of things constantly changing. How fast is the apple falling at this precise instant? What is the exact area under a continuously curving path? How do you sum up an infinite series of tiny changes? The old math was a dictionary for a world of nouns. It had no verbs. The existing mathematics was static, a set of tools for a frozen world. So, Isaac Newton invented a new language. He called it his method of fluxions, a name that beautifully captures its purpose. He envisioned quantities not as static values, but as fluents or flowing things, the rate at which they flowed, their instantaneous speed of change, he called a fluxion. What he had invented, what we now call calculus, was the engine needed to describe a world in constant motion. It provided two revolutionary tools: differentiation, the ability to find the precise rate of change, the fluxion at any given moment, and integration, the ability to find the total accumulation of that change, the area under the curve. For the first time, motion, acceleration, and dynamic forces were not just philosophical concepts. They were quantities that could be precisely calculated, predicted, and mastered. What if color, the most vibrant and fundamental quality of our visual experience, doesn't actually exist in the objects you are looking at? What if a rose is not red and a leaf is not green? This was the revolutionary, almost heretical, proposition Newton explored in his darkened room at Woolsthorpe for 2,000 years. The Aristotelian view held that color was a property of matter, a quality that objects possessed inherently. A ruby was red because it was a ruby. Light simply illuminated that redness. Newton suggested something far stranger and more profound. The objects themselves are colorless. They are merely filters. The color, the entire spectrum, exists only and entirely within the light that hits them. In his darkened room at Woolsthorpe, Newton performed one of the most elegant and decisive experiments in all of science, the experimentum crucis, or the critical experiment. He drilled a small hole in his window shutter, allowing a single, precise beam of sunlight to enter the darkness. He placed a prism in this beam, and just as others had seen before, the prism split the white sunlight into a beautiful, elongated spectrum of colors on the far wall, the rainbow. But Newton didn't stop there. He then took a second board with a small slit, isolating just one of those colors, for example, the pure red light. He then passed that isolated red beam through a second prism. According to the old theory, the prism should have modified or further colored the red light. It did not. The red light emerged as the same, pure, unchanged red. He had proven that the prism does not create the colors, it simply separates them. In a final, unassailable flourish, he used a lens to recombine the full, separated spectrum back into a perfect circle of the original white light. This discovery was not just a parlor trick. It immediately solved one of the most pressing practical problems in 17th century astronomy: chromatic aberration. The telescopes of the day, including Galileo's, used lenses to gather and focus light. Newton, through his prism experiments, now understood why their images were so blurry and fringed with color. A lens, like a prism, bends or refracts different colors of light at slightly different angles. Red light and blue light simply cannot be brought to the same perfect focus. This distortion was fundamental and unavoidable. Armed with this knowledge, Newton bypassed the problem entirely. He built a revolutionary new kind of telescope. Instead of using a lens to gather light, he used a precisely curved mirror made of polished metal speculum. A mirror reflects all colors at the exact same angle, eliminating the chromatic aberration completely. His small, powerful reflecting telescope, which he built himself, grinding the mirror by hand, stunned the scientific community and was his ticket into the prestigious Royal Society of London. How did a simple, mundane event, an apple falling from a tree in a garden, spark the single, unifying idea that governs the entire cosmos? The story of the apple is likely true, not as a moment of sudden discovery, but as a moment of profound questioning. Newton's genius was not in noticing that the apple fell. Everyone knew that. Gravity was an obvious, terrestrial phenomenon. His genius was in the question he asked next. If this force of gravity pulls the apple from the branch, does it also pull on the moon, orbiting high above? He wondered, how far does this force extend? Does it reach the top of the highest mountain? Does it, perhaps, extend infinitely, all the way to the moon and beyond? This was the conceptual leap that no one else had made, the unification of heaven and earth under a single, mathematical law. His genius was the breathtaking realization that the force pulling the apple to the ground is the exact same force holding the moon in its orbit. He performed a calculation. The apple falls towards the earth, and the moon is also, in a very real sense, falling toward the earth. The moon, however, possesses an immense sideways velocity, its inertia. So, as it perpetually falls towards the earth, the spherical earth continuously curves away from it at the exact same rate. The moon is, therefore, in a state of continuous, perfect, orbital freefall, always falling, but always missing. This single thought, this unification of the terrestrial and the celestial, shattered the 2,000-year-old Aristotelian divide between the corrupt, changing earth and the perfect, immutable heavens. It was one universe, and it all followed one rule. What if the single most important and influential science book in human history, the philosophy naturalist Principia Mathematica, was only published because of a friendly coffee-house wager and the appearance of a mysterious, terrifying comet? For years after his year of wonders, Newton kept his revolutionary discoveries in calculus and gravity largely to himself, a recluse at Cambridge, his mind diverted by the obsessive and secret pursuit of alchemy. But in 1680, a great comet later known as Kirk's Comet blazed across the European sky, its vast tail stretching across the zenith. This celestial spectacle terrified the public but electrified the scientific community. In London, at a coffee house, Three of the Royal Society's brightest minds, the brilliant architect Sir Christopher Wren, the cantankerous curator Robert Hooke, and the young, dashing astronomer Edmund Halley debated the comet's path. They had all begun to suspect that the force holding the planets in orbit followed an inverse square law, where the force drops off by the square of the distance. But none of them, not even the mathematically gifted Hooke, could prove that such a law would produce the elliptical orbits observed by Kepler years later. In August of 1684, the persistent Edmund Halley made a pilgrimage to Cambridge to pose this very question to the quiet, strange Professor Newton. He asked him directly, what path would a planet take if it were attracted to the sun by a force that decreased with the square of the distance? Newton, in a display of casual, world-changing brilliance, replied instantly, an ellipse. When Halley, stunned, asked how he knew, Newton replied, why, I have calculated it. He had solved this celestial problem years before, but couldn't find the calculations among his chaotic papers. He promised Halley he would redo them and send them along. A few months later, Halley received not just the simple proof, but a 9-page treatise titled Demo to Corporum Ingerum on the motion of bodies in an orbit. Halley was thunderstruck. This was not just a solution to his wager. It was an entirely new system of celestial mechanics. He rushed back to Cambridge and, with incredible diplomacy and flattery, begged Newton to publish everything he knew. This plea ignited an 18-month storm of obsessive work, culminating in the Principia. How did three simple rules, three short statements about motion, become the unshakable foundation for all of modern physics, all of engineering, and even the complex calculations required for space travel? Newton's three laws of motion, the core of his Principia, were so revolutionary because they were not mere qualitative descriptions like those of Aristotle. They were a predictive, mathematical system. For the first time in human history, the physical world was not just something to be observed, it was something to be calculated. Using these laws and his calculus, one could predict the future trajectory of a cannonball, the ebb and flow of the tides, the return of a comet, or the wobble of a planet. They transformed natural philosophy from a descriptive art into a quantitative, predictive science, giving humanity a power over the material world that, until that moment, would have been considered divine. Law 1, the law of inertia, states that an object in motion stays in motion, and an object at rest stays at rest, unless acted upon by an external force. This was a direct assault on the Aristotelian idea that the natural state of all things was rest. Law 2, famously expressed as $F equals mod dollar, force equals mass times acceleration, is the engine of all physics. It defines force not as a vague push or pull, but as a precise, measurable quantity, the rate of change of momentum. It is the mathematical key that unlocks the relationship between force, mass, and motion. And Law 3, the law of action-reaction, states that for every action, there is an equal and opposite reaction. This simple, elegant law reveals the universe as a series of balanced interactions. You cannot touch without being touched. It is this law that explains how a rocket can propel itself through the vacuum of space. By throwing mass out its back action, it is thrust forward reaction. These were not just descriptions. They were the mathematical blueprints for all motion. What if the most important science book ever written, the foundational text of our physical reality, was almost cancelled and left unpublished because of a failed, lavishly illustrated book about fish? This is precisely what happened. When Edmund Halley returned to the Royal Society, brimming with excitement about Newton's masterpiece, he was met with a devastating financial reality. The Royal Society, despite its prestige, was effectively broke. They had just invested their entire publishing budget, and then some, into a monumental, beautifully illustrated, and commercially disastrous tome, Francis Willoughby's De Historia Piscium, or A History of Fishes. The book had failed to sell, and the Society's warehouse was now full of unsold copies of a very expensive fish book. They had no money left to print Newton's dense, mathematically terrifying manuscript. The Royal Society, officially bankrupt from publishing A History of Fishes, regretfully informed Newton they could not fund his project. The entire Principia, the laws of motion, the law of universal gravitation, the unification of heaven and earth was dead on arrival. But Edmund Halley, in one of the greatest acts of scientific patronage in history, refused to let it die. He was not a wealthy man, but he believed in Newton's work with an almost religious fervor. Halley made an extraordinary decision. He would pay for the entire printing of the Principia 1687 out of his own pocket. He didn't just finance it. He served as editor, copy editor, proofreader, and, most critically, as a diplomat, constantly massaging Newton's paranoid ego and managing a furious priority dispute with Robert Hooke. Halley risked his own financial ruin on a book so mathematically dense that it was said only a handful of people in the world could even read it. How did the most rational, logical, and mathematical mind in human history come to spend more time, by a significant margin, studying magic, mysticism, and forbidden biblical texts than he ever spent on physics and mathematics? This is the central paradox of Isaac Newton. His collected papers, when examined, reveal a stunning truth. Of his roughly 10 million words of writing, over 1 million are devoted to the obsessive, secret study of alchemy. Even more are devoted to radical, heretical theology and the intricate, mathematical decoding of biblical chronology. To the modern mind, this is a bizarre contradiction. But to Newton, it was not. He was not a scientist in our sense. The word wouldn't even be coined for another 150 years. He was a natural philosopher, a seeker of divine truth. He believed the universe was a cipher, a great puzzle created by God. Physics and mathematics were one part of the code. Alchemy and the true reading of Scripture were the others. He was, in his own mind, simply trying to read the mind of God in all its forms. Secretly, Newton was an obsessive alchemist and a profound religious heretic. His alchemical work was not the cartoonish quest for gold. He was searching for the lapis philosophorum, the philosopher's stone, which he believed was not a thing, but an active vegetable spirit that God used to imbue matter with life and form. He saw it as the hidden agent of change that mirrored the gravitational force in the heavens. Far more dangerous, however, was his theology. After decades of intensely private, obsessive study of the earliest biblical texts, Newton concluded that the central doctrine of Christianity, the Holy Trinity, was a fraud. a great imposture inserted into the scriptures centuries after Christ by the corrupt Roman Catholic Church. He was a secret Arian or Unitarian, believing in one supreme God, with Christ as a subordinate, created being. To hold this belief in 17th century England was a capital crime, punishable by imprisonment, seizure of all property, and even death. He was, his entire life, a heretic hiding in plain sight. Most notably as a fellow at Trinity College, Isaac Newton was revered in his lifetime as a god of science, the man who had unwound the rainbow and calculated the heavens. But he was also a deeply, pathologically flawed man, the same obsessive, relentless, paranoid focus that allowed him to solve the riddles of the universe also made him a terrifying and vindictive enemy. He was incapable of collaboration, pathologically secretive, and saw any intellectual criticism not as a debate, but as a mortal, personal assault. His paranoia and his bottomless capacity for rage led to some of the ugliest, most destructive rivalries in the history of science, feuds that would tarnish his name and ruin the reputations of his rivals. He was a man who never forgave, never forgot, and used his immense power to systematically destroy anyone he perceived as an enemy. He battled his first great rival, Robert Hooke, for decades over priority in both optics and gravity. Hooke was the brilliant, if abrasive, curator of experiments for the Royal Society. He had indeed proposed an inverse square law for gravity before Newton, though he lacked the mathematical ability to prove it led to elliptical orbits. When Hooke requested even a simple acknowledgement in the Principia, Newton flew into a rage and, in a fit of spite, systematically deleted nearly every single mention of Hooke's name from the entire manuscript. But his most brutal and protracted war was waged against the great German philosopher and mathematician Gottfried Wilhelm Leibniz. Leibniz had, completely independently, invented calculus. His system was elegant, and his notation, the d, dx, and the integral symbol integral was actually superior to Newton's dotted fluxions, and it is Leibniz's notation we all use today. The question was not who had a valid system, but who was first. This priority dispute over calculus devolved into a vicious, nationalistic war that poisoned European mathematics for a century. Newton, in his later years, became the all-powerful, autocratic president of the Royal Society. He wielded this position like a weapon. To settle the dispute, he assembled a supposedly impartial committee at the Royal Society to review the evidence. In reality, he stacked this committee with his own loyalists and supporters, provided them with the evidence he had personally curated, and then, in an act of staggering intellectual dishonesty, secretly wrote the committee's final report himself. This report, the Commercium Epistolicum of 1712, was a piece of character assassination, officially declaring Leibniz a fraud and a plagiarist. He published it, and even wrote a glowing, anonymous review of his own report. He used the full institutional power of British science to destroy his rival's reputation, a vendetta he continued even after Leibniz was dead. How did the world's greatest living scientist, the quiet professor who had decoded the laws of God, transform himself into the world's most ruthless and effective detective, a man who would hunt counterfeiters through the slums of London and personally send them to the gallows? In 1696, after suffering a profound nervous breakdown, what he called a distemper of the head, Newton decided to leave academia and the isolation of Cambridge for a new life in London. Through his political connections, he was appointed to the position of Warden of the Royal Mint. This was not the ceremonial, sinecure post he had expected. He arrived to find a nation in the midst of a profound economic crisis. The currency of England was on the verge of collapse. Decades of clipping, criminals literally shaving the silver from the edges of coins, and rampant. Sophisticated counterfeiting meant the money in circulation was almost worthless. As Warden of the Mint, Isaac Newton left the world of abstract science and applied his obsessive, relentless genius to the world of criminology. He was not a gentle administrator. He was a hunter. He became, in effect, England's first great detective. He systematically reorganized the mint, implementing the great recoinage with mathematical precision. But his real passion became the pursuit of the counterfeiters. He donned disguises, going undercover into the bars, brothels, and dark alleys of the London underworld to gather intelligence himself. He tracked down informants, cross-examined witnesses with terrifying, cold logic, and personally built the cases against the criminal syndicates. His ultimate target was the brilliant, audacious counterfeiter and conman, William Chaloner. Chaloner was Newton's intellectual equal in crime, a man who had even testified before Parliament. Accusing the mint itself of corruption, Newton made it his personal mission to bring him down. Newton showed absolutely no mercy. He gathered his evidence against Chaloner with the same obsessive precision he had used to track the orbit of a comet. He turned Chaloner's associates against him, built an ironclad, inescapable case, and personally oversaw the prosecution, ensuring Chaloner was convicted of high treason. From his cell in Newgate Prison, a terrified Chaloner wrote desperate, begging letters to Newton, appealing to him as a gentleman and pleading for mercy. Newton received the letters and did nothing. He was implacable. He not only ensured that Chaloner was sent to the gallows at Tyburn, but he also personally attended the execution. He stood in the crowd and watched as his great adversary was hanged, drawn, and quartered. The man who had sought God's laws in the heavens had become the unyielding, terrifying instrument of man's law on earth. How did this one, solitary, complex man manage to single-handedly transform magic and philosophy into the rigorous, mathematical language that we now call physics? The answer is in the Principia. Before Newton, the universe was a place of qualities and purposes. A rock fell because its purpose was to be at rest at the center of the earth. The planets moved in circles because the circle was the most perfect shape. It was a poetic, philosophical world. After Newton, the universe was a place of quantities and laws. A rock falls because of a precise, quantifiable force $F equals G, CDOT meter _1, CDOTM _2, RE $ a planet moves in an ellipse. Because that is the mathematically necessary path dictated by the laws of inertia and the inverse square law of gravity, he gave humanity the grammar and the dictionary for a new reality. He made mathematics the language of reality. This was his most profound legacy. For the first time in human history, The universe was no longer an incomprehensible mystery, the whim of gods or spirits. It was a calculable system. It was a grand, intricate, clockwork universe, crafted by a divine watchmaker, as the metaphor went. God had created this system, wound it up, and set it in motion according to the deep, elegant, mathematical laws that Newton had been the first to discover. This deterministic worldview, the belief that if you knew the position and velocity of every particle, you could, in principle, calculate the entire future of the cosmos, became the bedrock of the Enlightenment and dominated Western scientific thought for more than 2 centuries. If I have seen further, it is by standing on the shoulders of giants. This is, perhaps, Isaac Newton's most famous quotation, a line that has become the very motto of scientific progress, a beautiful expression of humility, acknowledging that all discovery is built upon the work of those who came before. It is often invoked to show Newton paying his respects to the giants on whose work his own was built, figures like Galileo, Kepler, and Descartes. The quote first appears in a letter from Newton to his rival, Robert Hooke, in 1675. During a rare and brief period of reconciliation between the two men. But given Newton's character, was this truly a moment of profound humility, or was it, in fact, his most brutal and sophisticated insult? This famous letter was written to his rival, Robert Hooke, a man who was described by his contemporaries as being short, sickly, and physically deformed, possibly with a hunched back. From a severe case of kyphosis, was it possible that Newton, a man we know was capable of an almost sociopathic vindictiveness, was engaging in a cruel, sophisticated pun? I have seen further, because I stand on the shoulders of giants, unlike you, you little hunchback, who only claims to be a giant. Historians remain deeply divided on this very question. It is a perfect ambiguity, but in the end, the quote's origin and its possibly vicious intent has been eclipsed by its adopted meaning. It came to define the noble creed of science, that all progress is cumulative, that we all see further because of the work of our predecessors. The quote transcended the man who wrote it. Newton's laws were perfect. They were the laws of God. For over 200 years, they were treated as absolute, infallible dogma. They were used to predict the trajectories of cannonballs, the design of bridges, the spin of machines. And in their greatest triumph, they were used in 1846 to predict the existence and precise location of a brand new unseen planet Neptune based on tiny wobbles in the orbit of Uranus. Newton's laws were unassailable until, at the turn of the 20th century, they weren't. What happens when the architect's unshakable rules, the very foundation of physics for 8 generations, finally begin to crack and break? A tiny, persistent anomaly, a crack in the perfect facade, began to show. His laws failed at the most extreme scales, and the first conclusive failure was found in our own solar system. The orbit of the planet Mercury, the closest planet to the Sun's immense gravity, was misbehaving. Specifically, its elliptical orbit was precessing the whole orbit was slowly rotating at a rate slightly faster than Newton's laws of gravity predicted. The discrepancy was tiny, just 43 arcseconds per century, but it was measurable, and it was undeniably real. Astronomers tried desperately to save Newton, even inventing a hypothetical new planet, Vulcan, orbiting between Mercury and the Sun to account for the gravitational anomaly. But Vulcan was never found. The problem wasn't a missing planet. The problem was Newton's law itself. Then, in 1915, a young German patent clerk named Albert Einstein revealed a new, deeper reality. In his general theory of relativity, Einstein proposed that gravity is not a force pulling between objects, as Newton had said. Instead, gravity is a curvature in the very fabric of space-time. And planets are simply following the straightest possible path a geodesic through that warped geometry.